Hey everybody, welcome back. So we are continuing along with our command line basics. This is part 2. Initially we went through the first assignment. We got through navigating files and directories, so check those out if you haven't seen them yet. But now we're going to move on to working with files and directories. And I'm just going to move this to the side, and then we've got our terminal window over here. Cool. Okay. So how can I create, copy, and delete files and directories? How can I edit files? Create a directory hierarchy that matches a given diagram. Create files in the hierarchy using an editor by copying and renaming extension files. So, and then we want to delete, copy, and move specified files and or directories. So first off, creating directories. We now know how to explore files and directories, but how do we create them in the first place? In this episode, we will learn about creating and moving files and directories using exercise data and writing as an example. So let's list our things here. We want to change directories. If we do pwd, we should see that we're in the shell lesson data that we saved to our desktop. And so, yeah, if we do that, next we'll move to exercise data/writing. And so, yeah, we want to go to exercise data. So we change directories into exercise data, and we'll use tab completion to do it quickly. And then if we click tab again, we can see that there's a lot of opportunities here, so we want to go writing. And then we use tab to complete, and now if we do pwd, we'll see that we're in exercise data/writing. And if we do ls-f, we see we have Little Women and hiq.txt. That's interesting. Mine was in reverse order. So we want to create a directory. Let's create a directory called thesis using the command line make dir thesis. Okay, so make dir thesis. Now, if we do ls, you'll see that we have our thesis directory in here. And if we do ls-f, it shows that these two are text files, and this is a directory. So now, if we go ls-f thesis, this should give us blank because it's an empty folder. Note that make directory is not limited to creating single directories one at a time. -p option allows make dir to create directories with nested subdirectories. Oh, cool. Make dir -p /project /data and /project /results. So this is probably going to make 2 directories, both in the project file. So if we change directories back and we list out there and we change directories into project, it should have data and results. Cool. So we were able to do it twice with the -p command. The -r option to the ls command will list all nested subdirectories within a directory using ls-fr to recursively list the new directory hierarchy we just created for the project. Cool. So if we do it ls-fr ... /project. No, we're already at project, so we don't need to pass anything in. Well, that doesn't give us anything, but that's not especially interesting. Because of where we are. So let's say where we did this one, we were back in which folder? Thesis. So change directories, I think writing, and then thesis. And now if we do that, ls-fr, and then we pass in the project. So we want to change directories back, ls-fr /project. Yeah. Cool, that gets us that. And so that gives us project and then its related paths. And it looks like it shows us if there's things in there. Okay, 2 ways of doing the same thing. Using shell to create a directory is no different than using a file explorer in your open or current directory using your operating system's graphical file explorer. The thesis directory will appear there too. Well, what does that mean? If you were to go to your desktop, your shell lesson, you're going to find your writing. Your thesis folder is here as well. And your project files with data and results. So you could just add these there as well. So let's just say we wanted to make a directory here, new folder, test directory. If we were to run this again, now we see test directory is there. So there's nothing special about this versus using the graphic user interface. It's just that with typing, it's a little quicker. 2 ways of doing the same thing. Okay, yeah, so that's what that was about. Good names for files and directories. Complicated names of files and directories can make your life painful when working on the command line. Here we provide a few useful tips for the names of your files and directories. Don't use spaces. Spaces can make a name more meaningful, but since spaces are used to separate arguments on the command line, it is better to avoid them in names of files and directories. You can use dash or underscore instead. For example, she did the north like that rather than having the space. To test this out, try typing make dir North Pacific Gyre and see what directory or directories are made when you check with ls-f. Try typing. Oh, okay, I see what it's saying. So if we go make pwd. Okay, so we want to go back to maybe the main path, the shell lesson data. So what happens if we say make dir North Pacific Gyre? And now if we go ls-f, capital F, you can see we've got the North Pacific. We've got 3 separate files that open those up. So we've made 3 separate folders. To make it even more clear, you could see if you came into here. Yeah, we have this one, and wait, here we go. 1, 2, 3. So we've made 3 empty folders when we really went to make 1. Don't begin names with a dash. Commands that treat names starting with a dash as options. So don't use dashes and don't use spaces. Stick with letters, numbers, period, or full stop, dash, or underscore. Many other characters have special meanings on the command line. We will learn some of these during our lesson. There are special characters that can cause your command to not work as expected, and this can even result in data loss. If you need to refer to files or directories that have spaces, you should surround them with quotes. So what would that mean? Here we did that North Pacific Gyre. If we were to pass that in like this, we would have a folder that had spaces in it. Now, but if we did ls-f, you'll see that we have one with spaces in it, so that's possible. I think if you don't do f, then it's ls-a. Okay, cool. But for the purposes of this, we just made these all inaccurately, so I'm going to highlight them and delete them. Cool. Just to keep our stuff fine. All right. And then create a text file. Let's change our working directory to thesis. So pwd ls. Let's go change directories into North Pacific Gyre. Yeah. No. Exercise data. And then we want to change directories into thesis, right? No, writings. And then thesis. Okay, so now that we're in thesis, it says create a file called draft.tx. So we've changed directories into thesis, so now we can go nano draft.txt. Okay, so I did nano. All right. When we say nano, nano is a text editor. We don't really mean a text. It can only work with plain character data, not tables, images, or any other human readable media. We use it in examples because it's one of the latest complex text editors. However, because of this trait, it may not be powerful enough or flexible enough for the work you need to do after this workshop. Our Unix systems, such as Linux or Mac OS, many programmers use Emacs or Vim, both of which require some more time to learn, or a graphical editor such as Gedit. On Windows, you may wish to use Notepad++. Windows also has built-in editor called Notepad that can be run from the command line in the same way as nano for the purposes of this lesson. No matter what editor you use, you will need to know where it searches for and saves files. If you start it from the shell, it will probably use your current working directory as a default location. If you use your computer's start menu, it may want to save the files to your desktops or documents. You can change this by navigating to another directory the first time you save as. Let's type a few lines of text. Once you're happy with the text, you can press Control-O or Control+O or Control key, and while holding it down, press O to write our data to disk, and we'll be asked to what file we want to save to. Press Return to accept the suggested default. So this is just some random text. And now we're going to go Command-O. Oops. Control-O. File to write, draft, yeah. Okay, Control-O. And then we want to save it, press Return. Okay. Once saved, we can use Control-X to get out. All right. Once our file is saved, we can use Control-X to get out. Okay, so now if we go ls, we should see draft.txt. And I think you can go echo cat draft. It's just some random text. So yeah, the cat will just read the text in the file. The control key is also called the control CTRL key. There are several ways in which using the control key may be described. For example, you may see instructions to press the control key while holding it down, the X key, Control-X. In Nano, along the bottom screen, you'll see get help and O. This means that you can use Control-G to get help from Control-O. Nano doesn't leave any output on the screen after it exits, but ls now shows that we have created a file called draft.txt. Okay, creating a file a different way. This is definitely the way I like to create files. We've seen how to create text files using Nano Editor. Now try using the follow command. So touch myfile.txt. What did come? So it just pulled it out, right? When you look at your current directory, if we go ls, we see that my file is here now. It's a text file. Use ls-l to inspect the file. I didn't know you could do that. Oh, wow. When might you want to create a file this way? When you're going quick? When you just want to build the structure of your application? Touch generates a new command called myfile in your current directory. You can observe this newly generated file by ls in the prompt. It can also be viewed in your GUI file explorer. So if we were to come over here, where did we put it? Text. Was it thesis, right? Yeah. So draft, that one came from Nano, and then this one came from pressing touch my file. When you inspect the file with ls-l, note that the size of the file is 0 bytes. Yeah, here's the size of the file. In other words, it contains no data. If you open my file in a text editor using your text editor as blank, some programs do not generate output files themselves, but instead require an empty files that have already been generated. When the program is run, it searches for an existing file to populate with its output. The touch command allows you to efficiently generate a blank text file to be used for such programs. Okay, and then here's what's a name. You may have noticed that all of Nell's files are named something.something, and in this part of the lesson we always used the extension .txt. This is just a convention. We can call a file my thesis or almost anything we want. However, most people use two-part names most of the time to help them, and their programs tell different kinds of files apart. The second part of such a file is called a file name extension and indicates what type of data the file holds. .txt signals a plain text file. .pdf indicates a PDF document. .ctfg is a configuration file full of parameters or some other program. .png, for example, is a image. This is just a convention, albeit an important one. Files contain bytes. It's up to us and our programs to interpret those bytes according to rules for plain text files, PDF documents, configuration files, images, and so on. Naming a PNG image of a whale.mp3 doesn't somehow magically turn it into a recording of a whale song, though it might cause the operating system to try to open a music player when double clicking it. So if we're in here and we say touch whale.mp3, and then we come over here, you'll see that it wants to play it. So if we were to double click this, it's going to open up Apple Music. So that doesn't make a difference. The size of the file is just as tiny. What is it? ls-f, right? What was the one that formatted it properly? Oh, another cool thing about this is you can, if you're trying to find a command that you did in the past, just press up. Okay, cool. So that's the importance of naming it. And with the MP3, you can see it's still a blank file. It's just like my file, but because it has .mp3, the system immediately assumes that it's an MP3 file. Moving files and directories. Returning to the shell lesson data express writing. So if we go change directories, well, check out where we are. I think we could go shell directory, desktop, and then shell lesson data, and then exercise data, writing. Cool. I could have just gone cd ... on that one. In our thesis directory, we have a file called draft.txt. Cd thesis or ls thesis. We have draft.txt, yes. Isn't particularly informative name, so let's change the file's name using mv, which is short for move. So what we can do is say mv thesis, and then we've got draft.txt, and we want to change that to, does it tell us what it wants us to change it to? Quotes. So then we want to keep it in the same directory, so we do thesis, and then we do quotes.txt. Okay, cool. And now if we were to ls thesis, we'll see that here draft.txt is now gone, and there is quotes there. Yeah. One must be careful when specifying the target file name, since mv will silently overwrite any existing file with the same name, which could lead to data loss. An additional option is mv-i, or interactive, that can be used to make mv ask you for confirmation before overwriting. Now, note, mv also works on directories. Let's move quotes.txt into the current directory. We use mv once again, but this time we use it just the name of the directory as the second argument. Okay, so they're saying is mv, we've got our thesis, and then we can grab quotes, and where do we want to move that to? We want to move it to our directory where we are. Cool, so now if we list that, we've got quotes.txt in our current directory. The effect is to move the file into the directory, yeah. And now if we were to ls thesis, well, it's not blank because we put those two files in there, so we could remove those, but maybe we'll do that later with the terminal. Alternatively, we can confirm the file quotes.txt is no longer present in thesis. Ls with a file name or directory as an argument only lists the requested file or directory. If the file given as an argument doesn't exist, the shell returns an error, as we saw above, and we can use this to see the quotes.txt is now present in our current directory. ls quotes.txt, that gives us that. All right, moving files into a new folder. After running the following commands, Jamie realizes that she put the files sucrose.dat and maltose.dat into the wrong folder. These files should have been placed in the raw folder. So if we do ls-f, ls-r, analyzed in raw, what is it, dash recursively? So now I'm looking through this ls raw. Okay, so maybe they're just making something up. Fill in the blanks to move these files to the raw folder. So ls-f analyzed. Oh, I don't know. Circus data into the wrong folder name. These files should have placed the raw folder. So I think she would want to do period and then underscore raw. Double. Okay. So if she wanted to go up a one and then place those into that folder. Okay, cool. Let's moving on. Copying files and directories. The cp command works very much like mv, except it copies a file instead of moving it. We can check that it did the right thing using ls with 2 paths as arguments. Like most Unix commands, ls can be given multiple paths at once. So cp quotes.txt. Let's see if we're in the right file. Okay, it looks like we're not. Yeah, did it say? Okay, I think that they might just be giving us an example with this one. So if you were to copy quotes to thesis quotations.txt, quotes thesis quotation.txt. So we can also copy a directory. Wait a second. If we list here thesis. No, we want to be in writing. Change directories writing. ls thesis. Okay. So now I think we can say cp quotes.txt. So that's this local one to thesis dot / quotations.txt. And now if we were to ls here, we still have quotes. And then if we were to ls thesis and quotes, we would have thesis quotes. So it's quotations. So we've actually added to it. We can also copy a directory and all its contents using the recursive -r to back it up. So, yeah. Here we have thesis. We could go cp-r thesis, and then we could set that to thesis / underscore backup. And now, oh, okay. So up here, I missed the S here. Thesis backup. Now, if we were to list it, we have a thesis backup. So. And in there, we have all the files that we had in there originally. Cool. So that's how we can recursively copy directories and everything in them. Renaming files. Suppose you created a plain text file in your current directory to contain a list of statistical tests you will need to analyze your data. And you named it statistics.txt. After creating and saving this file, you realize that you misspelled the file name. You want to correct the mistake. Which of the following commands would you use to do it? You wouldn't want to do this because then you would keep the old one in there. So you could use this one and then delete the other one. You could move it like that. If you just moved it like that, I don't think that that would do anything. That would just move it to the same place it was. Statistics. And this wouldn't do it either. This would just rename it maybe with the same name. So, okay, cool. I got it right. It was no, yes, no, no. Cool. Moving and copying. What if the output of the closing ls command is the sequence shown below? All right, so you print your directory. You're in users Jamie data. You list it. You've got proteins with proteins spelt incorrectly. In your bash, you could make directory. So now you recombined, and then you move proteins to recombined. Okay, so now recombined has your proteins data file on it. And now you copy recombined proteins to proteins-saved data, ls. Cool, so now you'd have a recombined, and then on your root directory, you'd have proteins.data. Cool, what's the solution? All right. That's kind of hard to wrap your head around. Okay, so removing files and directories. Returning to the shelf lesson data exercise writing directory. Cool, that's where we are right now. Let's tidy it up a bit, the directory, by removing quotes.txt file we created. So rm quotes.txt. We confirm that it's gone by ls. Cool. Quotes is not there anymore. And if we try to do ls quotes, we'd get a no error. Deleting forever. The Unix shell doesn't have a trash bin that we can recover deleted files from, though most graphical Unix do. Instead, when we delete files, they are unlinked from the file system, and their storage space on the disk can be recycled. Tools for finding and recovering deleted files do exist, but they're no guarantee they'll work in any particular situation, since the computer may recycle the file's disk space right away. Using rm safely. What happens when we execute rm-i? Why would we want to do this? rm-i. Why? So let's touch whatever hi.txt. If we list it, we see it there. rm-i. And I'm going to empty my trash can real quick, just because my guess is that it goes to the trash. Hi.txt. Oh, so it just gives us the option. Remove it? Yes. Okay, so now if we list it, it's not there. And it did not go to the trash can. So -i just makes it so it asks its option to make it so you want to be yes or no. It's like a confirmation page. If we just try to remove the thesis page, we get a thesis as a directory. That happens because rm by default only works on files, not directories. Rm can remove a directory and all its contents if we use -r, and it will do so without any confirmation prompts. Given that there is no way to retrieve the deleted files in the shell, rm-r should be used with great caution. You might consider adding interactions with r and I. Yeah, but I mean, I don't even think that that's a good idea. I mean, maybe sometimes you want to be able to do that. Operations with multiple files and directories. Oftentimes, one needs to copy or move several files at once. This can be done by providing a list of individual files names for specifying a naming pattern using wildcards. Copy with multiple file names. For this exercise, you can test the commands in the shell lessons data exercise data. So where are we? So we can change back. Okay, if we just go back one, we'll be in exercise data. In the example below, what does cp do when we give several file names and directory names? So make directory, have backup. If we list that, we can see that backup is here. And then we want to copy creatures minotaur.data to creatures unicorn.data to backup. So my guess is that it copies both of these to that. So ls-r backup. It copied them both there. And then if we list our current one, if we list creatures, we should see minotaur and data. We should see minotaur and unicorn still there. So yeah, it copied both of them to there. So that way, so now you know you can copy multiple files to the same folder. If given more than one file name in the following directory, cp copies the files to the named directory. If given 3 file names, cp throws an error, such as the below, because it is expecting a directory name as its last argument. That's not very powerful. All right. Okay, using wildcards for accessing multiple files at once. The star symbol is a wildcard, which matches 0 or more characters. Let's consider the shell lesson data exercise data / proteins directory. *-pbd matches all the files that end with .pbd. On the other hand, p* only matches pentane and propane, because p at the front only matches the files in the letters. Yeah. Let's see here. So ls proteins, and then we go *-pbd. Okay, so that didn't work. Proteins. Let's make sure that's in there. Yeah. So wildcard. Okay, cool. Wildcards can be used in combination. When the shell sees a wildcard, it expands the wildcard to create a list of matching files names before running the command that was asked for. As for an exception, in a wildcard expression does not match any file, bash will pass the expression on as an argument to the command. For example, typing ls proteins. Well, let's just change directories proteins. And now if we just ls star dash bb bdb. Cool, that just gives us the ones with that, but if we do star with a P, that just gives us the 2. And I think this is some regex stuff. Results in an error message that there is no file called PDF. Yeah, so lsp, star dot. So list all of our PDFs. There's no matches. There are no PDF files in there. However, generally, commands like wc and ls see the lists of file names matching these expressions, but not the wildcards themselves. It is the shell, not the other program, that deals with expanding wildcards. When run in proteins directory, which ls command will produce this output? ethane.pbd and methane.pbd. Oh man, I don't even know. What does this one do? Octane and pentane. That one did even more. Ethane.pdd. No. I mean, actually, I think it's number 3. Methane. Wow, it's number 3. All these other, and this one might not match anything. Yeah. Anyways, it's number 3. So I guess these are THANE, but I don't know, because it would work also. You could just be like match star THANE dot PBD. Okay, so maybe you need that dynamic wildcard in there. Shows the files whose name contains 0 or more characters, followed by the T, then 0 or more characters, followed by the ane.pbd. This gives ethane, methane, octane, and pentane. Number 2 shows all the files whose names start with 0 or more characters, so that's what this star means, followed by the letter T, then a single character, then NE, followed by 0 or more characters. This will give us octane, penthane, and doesn't match anything which ends in thane.pbd. Number 3 fixes the problem of option 2, matching the 2 characters between T and NE. This is the solution. So yeah, the 2 question marks make it so that it requires that there's 2 letters in the name of the file. And only shows files starting with ethane. So more wildcards. Here we've got some more. Sam has a directory containing calibration data, datasets, and descriptions of data. Before heading off to another field trip, he wants to back up her data and send some datasets to her colleague, Bob. Sam uses the following commands to get the job done. Okay, so she's copying the dataset to backup datasets. She's copying calibration backup dataset. She's copying it to another one. She's copying send a bit to Bob. So she wants to add this to this here. Help Sam filling in the blanks. Resulting directory structure should look like this. Okay, help Sam by filling in the blanks. She's copying the dataset to backup datasets. So she's copying something calibration. I don't know how she gets that. That's really tricky. I don't really care about understanding this. Okay, so she wants to star the calibration.txt 2015-11 star Bob's start underscore dash 23. That way she's just send to Bob. So she's copying it all to a single folder. Cool. Directories and files, ls-f. Jamie is working on a project and sees that her files aren't very well organized. ls-f. Raw, fructose. Fructose and the Circos data contain output from her data analysis. What command covered in this lesson does she need to run so that her commands below will produce the output shown? ls-f, analyzed raw, ls analyze, fructose and data. So what she needs to run is copy fructose.dat space circos.dat space analyzed / Oh, she could do that too. Oh, move. Yeah, moving would be better. Otherwise, you'd have a copy. Produce a folder structure. Okay. Reproduce a folder structure. You're starting a new experiment. You would like to duplicate a thing, ls. Let's change directories back to the exercise data. No, we'll go back. This one, folder structure. Okay, so here. Assume the previous experiment in the folder called 2016-518, which contains a data folder that in turn contains folders named raw and processed that contain data files. The goal is to copy the folder structure of 2016-518 folder into a folder called 2016-5-20 so that your final directory structure looks like this. Which of the following sets of commands would achieve this objective? What would the other commands do? Okay, this one makes the file, it makes the subfolder, and then it makes these. So this would work. It just makes them all. That's very explicit. So here we change directories into it, and then we make directory of data, and we change directory of data, and we make directory of raw and processed. This one would work as well. Here we make all three of the, we make them all twice. This one works as well. This one would work as well, I think. This one might not work because it needs to have a P on it. Make directory, change directories. This one would not work because you would need to change directories into data. So, yeah. The first two sets command achieve this objective. The first set uses the paths to create a low-level directory and the subdirectories. The third set of commands will give you an error because the default behavior of make directory won't create a subdirectory of an existing one, right? Because you need to pass in that -p command. The fourth set command achieves the objective. So, yeah. 1, 2. This one's good. This one good. This one didn't, like we said, because it didn't have the P. This one does because it has the P, and this one won't. The final one generates the raw and process directories at the same level as data directory. Yeah. Okay, cool. Our key points, copy old to the new copies of a file, make directory with a path, creates a new directory, move, and you take the old file to the new file. That is moves the file. RM removes the deletes data. The star matches 0 or more characters in the file name. And so it's kind of like a regex-like thing. Question mark matches any single character in the file name. So it would match a.txt, but not any.txt. Use control keys may be described many ways, including control X, and then up-X. So the shell does not have a trash bin. Once something is deleted, it's really gone. Most files names are something.extension. This extension isn't required and it doesn't guarantee anything, but it normally used to indicate the type of data in the file. Depending on the type of work you do, you may need a more powerful editor than Nano. And we do. We have Visual Studio Code. Okay, cool. So if we move on, pipes and filters. So this looks like another kind of long one, pipes and filters. And we want to make sure we're doing that one. Cool. This is the last one of this section that the Odin Project wants us to work on, so we don't really have to understand loops, shell scripts, and final. So we can go straight into pipes and filters. Okay, pipes and filters. I'm going to press Command K over here and clean this up. How can I combine existing commands to do things? Redirect a command's output to a file, construct command pipelines with 2 or more stages, explain what usually happens if a program or pipeline isn't given any input to process, explain the advantage of linking commands with pipes and filters. Now that we know a few basic commands, we can finally look at the shell's most powerful feature, the ease with which it lets us combine existing programs in new ways. Let's start with the directory. So we, it looks like they want us in exercise data proteins. So if we go pwd, you can see we're in the shell lesson data. So we're going to change directories to exercise and then proteins. Cool. This contains 6 files describing the simple organic molecules. The .pdb extension indicates that these files are protein data bank format, a simple text format that specifies the type of position of each atom in the molecule. So if we ls proteins, okay, so yeah, if we ls that here, that just gives us our proteins, and that gives us these 6. Let's go into the directory and run the simple command wc cubane. Okay, wc is word count command. It counts the number of lines, words, and characters in the file from left to right in that order. If we run wc pdb, the pound in pdb matches 0 or more characters, so the shell turns pdb into a list of all pdb files in the current directory. wc.pdb needs to be wc. Okay. Note that wc-pdb also shows the total number of all the lines in the last output. Oh, cool. So that's like the sum up everything. If we run wc-l instead of wc, the output shows only the numbers of lines per file. Oh, well, that's super useful, I guess. The -m-w options can also be used with wc command to show only the number of characters or the number of words in the file. Why isn't it doing anything? wc-l. Okay. I press Control-C to stop it. What happens if the command is supposed to process a file, but we don't give it a file name? For example, what if we type wc-l, but don't type wildcard pdb after the command? Since it doesn't have any file name, wc assumes it's supposed to process input given at the command prompt. So it just sits there and waits for us to give it some data interactively. From the outside, though, all we see is it just sitting there. The command doesn't appear to do anything. If you make this kind of mistake, you can escape out by simply holding down the Control key and typing the letter C, or letting go to the Control-C plus C. Okay, capturing input from commands. Which of these files contains the fewest lines? It's an easy question to answer when there are only 6 files, but what if there were 6,000? Our first step toward a solution is to run the command wc-l, and then we're checking out all the .pdb, and then we're going to organize them by lengths.txt. The greatest tells us, okay, so that did nothing. Oh, but now lengths is there. So what happens if we go cat lengths? Oh, it tells the shell to redirect the command's output to a file instead of printing it. Oh, okay, to the screen. This is why there is no screen output. Everything that wc would have printed has gone into the file instead. The shell will create a file if it doesn't exist. If the file exists, it will silently overwritten, which may lead to data loss and thus requires some caution. ls lengths confirm the file exists. We can see it in here. So yeah. Yeah, it's there. We can now send the content of lengths.txt to the screen using cat lengths.txt. Okay. Cat command gets its formations, concatenate, i.e. together, and it prints the files after one another. The only one file in the case, so cat just shows us what it contains. And so it looks like it contains the same thing. Output page by page. Okay, so what's the main thing here? Capturing output from commands. So that's basically what we're learning here, is that you can write your output of a file into a command. Okay, so filtering output. Next, let's sort the command of sort the contents of lengths.txt. But first, let's use an exercise to learn a little bit about the sort command. What does sort-n do? The file show lesson exercise data numbers.txt contains the following lines. 10. Really? Cat. Exercise data. Sure. Exercise data. Okay, that's right. If we run sort on the file output, if we run sort-n, why does n have this effect? Sort's not a flag. I don't understand how you can run that. Oops. Is it like that? 10, 19, 2, 22, and 6. If we run sort-n, it's in the right order. N probably changes it to an integer, whereas it translates those directly to a string. You notice how it's 1, 2, 2, 6. The first digit's the highest one. Those are almost in some sort of alphabetical order. Specified numerical order rather than numerical. Got it. Okay. We will use -n option to specify that sort in numerical instead of alphanumerical. This does not change the file. Instead, it sends the sorted result to the screen. Okay, cool. So if we wanted to get the sorted result and we could get it to another one, then we could do it that like sorted length. Yeah. And that's what the instructions are about to say. After the command, we can use sort lengths.txt to put the output of OCC to lengths.txt. Once we've done that, we can run another command called head to get the first few lines in the sorted lengths. Oh, cool. Head-n the sorted lengths. I think you need to pass a number in, too. So there you go. And it's supposed to be 9. Interesting. Okay. Redirecting to the same file. It's a very bad idea to try to redirect output and command to the same file, for example. Doing something like this may give you an incorrect result or delete the contents of lengths.txt. Cool. And what does the double one do? We have seen the use of one, greater than symbol, but there is similar operator double greater than symbols, which works slightly differently. We'll learn about the differences between these two operators by printing some strings. We can use the echo command to print strings. Okay, so I'm going to change directories into the root one because this seems like it's going to just create a lot of trash. So here, if we run echo, the echo command prints text. The echo command prints text. Now test the command below to reveal the difference between the two operators. Okay, so yeah, we've created this test file.01. And now if we go echo. Uh-oh. This should have been hello. Echo hello test file.txt. Hmm. Okay, cool. Let's see if we do echo hello test file.txt too. Now we do cat test file.txt. Okay, cool. So yeah, I think this would add to the file, and whereas this rewrites it. If we do hello to test file 1, and then we cat test file 1. No, it doesn't work like that. I wonder what the answer is. In the first sample with that, the string hello is written to test file 1, but the file gets overwritten each time you run it. We see from the second example, the operator writes hello in it to the file, but appends the string to the file if it already exists when we run it for the second time. Cool. So the difference is one rewrites the file with this, whereas this one appends it to the end. Appending that. We have already met the head command, which prints lines from the start of the file. Tail is similar, but prints lines from the tail of the file. Consider shell lesson data, CSV. So we're in there. So if we were to tail-n2 exercise data, animal counts, animals.csv, that should just give us the last two. Whereas if we did it with head of a numbers of 3, we're going to get these 3. So that should be our solution. The first 3 lines of animal.csv, right, 2. The last 2 lines of animals.csv, right. The first 3 lines and the last 2 lines of animal.csv. The second and third lines. It's going to give us the last 2 and the first 3. The first 3 and the last 2. Yeah. And we could have done it in a pipe instead of doing it like this. We could have also done it like tail-n to exercise data, animal count, animals. And that would have gotten us this one and this one. That's a pipe. So passing output to another command. Cool, I'm going to clean this up. In our example of finding the file with the fewest lines, we are also using 2 immediate files, text lengths.txt and sorted lengths.txt, to store output. This is a confusing way to work because even once you understand what WC, sort, and head do, these immediate files make it hard to follow what's going on. We can make it easier to understand by running sort and head together. So where do we have this? Where do we have this lengths.txt? Oh, we created that. So here we sort the lengths.txt by the head and then the methane, and we get methane. So that must be the longest one. The vertical bar between the 2 commands is called a pipe. It tells the shell that we want to use the output of the command on the left as the input of the command to the right. This has removed the need for sorted lengths file. Combining multiple files. Okay, so yeah, being able to do this makes it so you didn't have to make that, copy it, and then remove it. You can just pass that in. Copying multiple files. Nothing prevents us from chaining pipes consecutively. We can, for example, send the output of WC directly to sort and then the resulting output to the head. This removes the need for any intermediate files. We'll start by using a pipe to send the output of WC to sort. Okay. WC-L pound. No, we need to be in the right place for this. This is going to be exercise data. Proteins. Okay. So now if we were to go WC-L pound.pbd sort by n. Oops. PDB. Okay, so now we're getting that. Yeah. So we moved to the right folder, and now we're getting the results that are expected in our proteins folder. It doesn't really say to do that to go up here. We can do that through another pipe to head, so the full pipeline becomes wc.l pdb sort-n, and then we just go head-n-1. 9 methane. This is exactly like a mathematical nesting function like log 3x and saying log of 3 times x. In our case, the calculation is head of sort of line count times TDD. The redirection pipes used in the last few commands are illustrated below. Cool, so it pulls out that, it gets the output, and then it retrieves the lengths, it sorts them, and it grabs the first one. Piping the commands. In our current directory, we want to find the 3 files which have the least number of lines. Which command listed below would work? wc-l, we get all the files. We want to sort by, you want to sort them by least. I think n would work. You want to get head of 3 with n. Okay, so I don't really know. This seems like pretty interesting. Option 4 is the solution. So we get all of them, we sort them negatively, and then we just select out the 3 based on their numerical values. Try it in the shells exercise proteins one. Okay, so wc-l sort-n head-. All right. Maybe that's right. Okay, so these are tools designed to work together. The idea of linking programs together is why Unix has been so successful. Instead of creating enormous programs that try to do many different things, Unix programmers focus on creating lots of simple tools that each do one job well and that work well with each other. The programming model is called pipes and filters. We've already seen pipes. A filter is a program like WC or sort and that transforms a stream of input into a stream of output. Almost all of the standard Unix tools can work this way, unless told to do otherwise. They read from standard input, so something with what they've read and write to standard output. The key is any program that reads lines of text from a standard input and writes lines of text standard output can be combined with every other program that behaves this way as well. You can and should write your programs this way so that you and other people can put those programs into pipes to multiply their power. Pipe reading comprehension. A file called animals.csv in the lessons exercise data animal count folder contains the following data. Cool. D data cd, and then we change directories into the animal counts. And then we can cat the animals. Looks like that's right. What text passes through each of the pipes and the final redirect to the pipeline? Note that sort-r command sorts in reverse order. So here we go. Animals.csv, so they're taking the first 5. 1, 2, 3, 4, 5. So all of these guys. And then we're taking the tail of those 3, so we're taking these 3. And then we're sorting in reverse. So 2, 7, 19. And you put it out to the final one. So it's going to be deer, raccoon, rabbit. Deer, raccoon, rabbit. Oh, and it sorted them by alphanumerical rather than the number. So this would have been better to do. I think you could probably go, instead of sorting it by R, sorting it by N. Numerical order. That didn't work. Huh. Animals. Animals.csv. Head. Sort-r final txt. Huh. Okay, cool. So pipe construction. For animals.csv, for the previous example, consider the following command. cut-d-f animal csv. Oh. The cut command is used to remove or cut out certain sections of each line of the file. Expects the lines to be... Oh, cool. It's cat animals. Look at that. It just was able to cut -f in position 2, animals.csv. Separated into columns by a tab. A character used in this way is called a delimiter. In the example above, we use -d option to specify the comma as the delineator. The -d means comma. We have also used -f option to specify that we want to extract the second field. That gives the following data. Okay, cool. So cut -d changes this all to comma separated values. And then the -f and that 2. 2 means this is probably 1 and this is 2. The unique command filters out adjacent matching lines in a file. How could you extend this pipeline using unique and another command to find out what animals the file contains without any duplicates? Are there duplicates? Oh. I guess you could go like I wonder if you could go that. Oh, the D and the comma's there, so dash unique. Oh. Maybe unique. Yeah, add unique at the front. Oh, okay. Sort unique. Sort unique. Cool. Which pipe? The file's animal CSV contains 8 lines of data formatted as follows. The unique command has a -c option that gives you a count of the number of times a line occurs in its input. Assuming your directory is shell lessons data animals count, what command would you use to reproduce a table that shows the total count of each type of animal in the file? Okay, this one doesn't seem like it works. What if we cat animals.csv? We see rabbits here like 22 and 16. And so up here, it didn't get us unique ones. So what does this one do? It sorts it. I don't know what -t is, -k. It puts them together, but it doesn't make them count by the numbers. This one tells us how many times, gives us a 1, and then it doesn't even count for the unique, so that one's not good. Got this one. I think that's the one. So cut -d, so -d with the comma. So it divides it by the comma, and then we take f of the first 2 animals, we sort them by unique in the C. And that one just doesn't do it. So yeah, 4 looks to be the answer. That's correct. If you have difficulty understanding why, try running the commands or subsections of the pipeline. Yeah, so what happens if we just do this? Okay, that just gives us all of them. And then we sort them so that they became the same. And then with the unique counter, when we pipe on the unique, I think that does the part where it adds it up. Rabbit 3, fox 1, and 2 deer. Okay, cool. And how they come up with the unique -c, I wonder if you could be like unique help. And then you've got your different things here. I think you actually need -- help here. And then -c, does that tell you how? Huh. Well, it is in there, so I guess you could play around with it to figure it out. Nell's pipeline. Okay. Nell has run her samples through the Asai machines and created 17 files. North Pacific Gyre, described earlier as a quick check starting from shell lesson data directory. Nell's types. CD. All right. CD North Pacific Gyre, and then we go WC-L.T. XT. Okay, so I think that just lists them out. Now she types this. She sorts them by the head. This is just going to print something else out. With a limit of 5. So the top 5 based on the sort of that. Okay, so there are files in 60 lines shorter than the others. When she goes back and checks it, she sees that she did the essay at 8 on Monday morning. Someone was probably using the machine on the weekend and she forgot to reset it. Before rerunning the sample, she checks to see if there's too much data. So why did she run this? 504, like she gets those ones. These numbers look good, but what's the Z doing there? Third to last line, so this one right here. All of her samples should be marked A or B by convention. Her lab uses Z to indicate with missing information. To find others like this, she does this. So yeah, she's just sliced out all of the ones with Z.txt, and she finds that there's 2 of them. Sure enough, when she checks the log on her laptop, there's no depth record of either of these samples. Since it's too late to get the information any other way, she must exclude those two files from her analysis. She could delete them using RM, but there are actually some analyses she might do later where depth doesn't matter. So instead, she'll have to be careful later and select the wildcard expression. Suppose you want to delete your processed data files and only keep your raw files. The processing script should you use? You definitely don't want to use this one. Definitely don't want to use this one. You'll remove all the text files. I don't think you want to use this one. And you don't want to use this one. I don't think any of these solutions are right. This would remove .txt files with 1 character names. Yeah, that doesn't help. There's no 1 character name ones. This is the correct answer. RM. So, oh, she wants to just get rid of them all. Oh, okay, I see what's saying. All right. So key points. WC counts lines, words, and characters. Cat displays the contents. Sorts the input. Head displays the first 10 lines of the input. Tails displays the last 10 lines. Command with a single one redirects a command's output to a file, overwriting the existing one, whereas this one does not overwrite the existing one. If you do first with a pipe in there, the output of the first command is used as the input to the second command. The best way to use the shell is to use pipes and to combine single-purpose programs. Awesome. I feel like that was useful. I've really brushed up on my Unix there. And we'll keep moving on. Let's see here. So that's the command line basics. That's our number 1 assignment. I don't know exactly how we could keep track of this, but this is going to be considerably longer. So I'm going to wrap this up in a 3rd video. But next time we'll be moving on to, with your newly discovered CLI superpowers, practice creating a folder and a few files using all the things that we different did. So we'll do that in the next lesson. We'll get started with that in the next lesson. Thank you guys for watching, and we'll see you later.